So we are going to talk about question 1 now, okay? And then as you see is that in the slides, we have 9 questions. So these are different types of questions might come in the KC calculations, okay? For the last 10 minutes, I just want to show you question 1. And if we have time, I can show you these 2 applications, okay? Just talk about these 2 processes and then how the temperature and the pressure affects their equilibrium, okay? So when we look at the question 1, a 2 grams of sample of ammonium hydrogen sulfide, okay? If you look at here, NH4HS is ammonium hydrogen sulfide. That's the only candidate can give us, only formula in this equation can give us this name. It's easy to see, okay? Is sealed in, okay, because it is a solid, okay? It's sealed because you want to make a closed container, closed system. That's why. Sealed in a 2 decimeter cube flask at a temperature of 375 Kelvin degrees, okay? It dissociates. Dissociates means broken down into simpler structures like H2S, hydrogen sulfide, and NH3, ammonia, okay? And at equilibrium, it's found that the concentration of ammonia is equal to 1.82 times 10 to the power of negative 3. So what is the question here is that you put 2 grams of this, and then after a while, you produce some of these 2, and then they reach equilibrium. When they reach equilibrium, the concentration of NH3 is 1.82 times 10 to the power of negative 3. So what happens here is that it's a very easy question. I'm going to show you why, okay? Like you remember this table, I just showed you this table, okay? We know the ratio. So what is given? Initial amount of NH4HS is given, and then the equilibrium concentration of NH3, okay? Can I just show you here? NH3 here, you can see the product, equilibrium concentration of product is given, okay? And then there is one point that we need to know. We just use the mole ratio. You remember we use the mole ratio, okay? And then we can also use the mole ratio here. It looks like we can use the mole ratio here, okay? So, which means that, okay, look at here, 4.8 moles of C produced, okay? What is the mole ratio? 1 to 2, 0.96 moles, okay? Moles of B used, okay? 9.6 moles of B used, okay? And then 4.8 moles of A used, okay? So I'm going to use the similar ratio here, okay? When I look at here, if 1.82 times 10 to the power of negative 3 mole per decimeter cube of, okay, concentration of NH3 produced, how much, okay, what will be the, or how much, or what will be the concentration of H2S, hydrogen sulfide, at concentration, so at equilibrium? How can I find that? I can use mole ratio, okay? Mole ratio. So what is the mole ratio between NH3 and H2S? 1, as you can see from the formula. So if I produce 1.82, so 82 times 10 to the power of negative 3 moles of NH3, how much H2S will be produced? 1.82 times 10 to the power of negative 3 moles, okay? And the concentration will be the same. Why the mole ratio and the concentration ratio will be the same? Because they have the same volume. Look at the formula on the right-hand side. C is equal to N over V. If the volumes are equal, okay, you can say the volume ratio will be equal to concentration ratio. So, which means that you are going to have same concentration of H2S and NH3 at equilibrium. So I can use this concentration ratio as mole ratio, okay? So now I know the concentration of H2S at equilibrium. Do I need to know the concentration of NH4HS? No, it is solid. So what is the first question? Calculate the equilibrium constant for this reaction. How can I write Kc formula for this equation? Very easy. So concentration of products, as you can see, H2S. What is the coefficient in front of it? 1. Concentration of product. What is the coefficient in front of it? 1. Okay, divided by. What is the concentration of reactant? Can I write down this? NH4HS in the formula? No. Why? Because as you can see, it is in solid phase. What we said at the beginning, I'm going to back to this, okay? Only aqua and gas in the formula, not solid and liquid. If there is solid and liquid, what do? We don't write it down, okay? So there is nothing in the denominator, one, just one, okay? So divided by one, there is nothing in the denominator. You don't put it in the formula, okay? And Kc formula is going to be equal to concentration of hydrogen sulfide to the power 1 and the concentration of ammonia to the power 1. And what are the concentrations? Same, we said 1.82 times 10 to the power of negative 3 times 1.82 times 10 to the power of negative 3. And that's going to give us 3.3 times 10 to the power of negative 6. And what is unit for Kc? No unit, okay? It's just a ratio. And then this Kc tells me that it is very small, okay, when you compare with one, smaller, much smaller than one. So which means that the product, it's not going to give us a large yield, it's going to give us a low yield, okay? So the next one, okay, 1.2, it's found that repeating the experiment at higher temperature. Concentrations, why are the concentrations equal? Okay, because imagine that you put 2 grams here into the container, okay? Why the concentrations of H2S and NH3 is equal? Because you put 2 grams of H2NH4 HS. So initially how much H2S and NH3 do we have? 0 and 0. So how much produced, NH3 produced, okay, is going to give us the number of moles of, okay, NH3 at equilibrium, isn't it? Okay, and how much H2S produce will give us number of moles of H2S will be at equilibrium, okay, because initial amount is 0. So which means that how do I know how much moles of H2S and NH3 produce? By using mole ratio, and then their mole ratio is 1:1. If the mole ratio between this one and this one is 1:1, this one is also 1:1. So if this one 1.82 times 10 to the power of negative 3 moles is produced, and this one is going to be 1.82 times 10 to the power of negative 3 moles, okay? Similar to that, and if the volumes are same, and it will give us the same concentration, okay? So they will be produced same amount of moles, and the concentrations will be same at equilibrium. So concentration ratio is equal to volume ratio. So that is why their concentrations are equal. And what is 1.2? Okay, it is found that by repeating the experiment at higher temperature, the equilibrium constant increases. How is it possible equilibrium constant increases? So the reaction must favor which reaction must be favored? Forward reaction. Why? Because if one of these H2S and NH3 concentration increases, the Kc will increase, okay? So I can easily tell you that forward reaction is favored, okay? Is the forward reaction exothermic, endothermic? Okay, I'm looking for that. So I increase the temperature, higher temperature, which means I increase the temperature. According to LCP, what will happen? Okay, according to LCP, what will happen? The reaction will decrease the temperature by favoring endothermic reaction, okay? So what happened to the Kc value? Increased, and endothermic reaction is favored, which means that forward reaction is endothermic, okay? One more time. To obtain, okay, to obtain a larger Kc value, okay, more H2S and NH3 should be produced. Yes, you can see from the formula. According to LCP, when I increase the temperature, okay, it will favor the one that decreases the temperature. It favors the endothermic reaction. And then if the Kc is increased, okay, Kc is increased, forward reaction is favored. Okay, if the temperature is increased, and the endothermic reaction is favored. So forward reaction is favored, endothermic reaction is favored, which means that endothermic reaction is forward reaction, or forward reaction is endothermic reaction. Okay, that's how we understand. Therefore, and the delta H for this reaction will be more than 0. Okay, it looks like time is up. Okay, what I will do is that, inshallah, I will try to, okay, can I just stop here recording?